So if my friend didn't pop up on my Facebook, and I got a weird
Did it fall?
You gotta twist.
Wait, what if you like lean it against this part too? Or is it?
Twist the back leg more. You need to make it like more of a.
I don't know if it's.
Here, do you want me to go aside? Can you split it? Does it see?
Yeah. That's fine. Like, what if we just had like lecture capture? What a crazy idea. Well, no.
You have a new homework posted. Some of you have noticed it. I think the TA and I got our wires crossed, and I thought he was gonna like blast out an email, and he thought I was gonna blast out an email, but it is there. It's listed as being due a week from today. I'm gonna push it back to 24 hours. It'll be due next Friday at midnight. It should be medium length. Today we're going to wrap up divide and conquer through another example, selection problem, and then we will do a crash course review on priority queues and heaps, which are relevant to your homework.
I was just about to say.
The last one, this is a little shorter than last one. Okay, so here's a problem for you. I give you n elements in arbitrary order. They are comparable. You can order them, but they're not sorted. And I asked for, let's make it concrete. So you guys each have a GPA. I want to know the median GPA among all of you. What's the best? Give me some ideas on how you might try to solve that problem. Don't even worry about it being the best. Just understand what we're asking for? Yeah.
The most obvious one, sort it, and then the middle.
Yeah, you could sort it, and we'll end up in a sorted sequence. Let's say it's an array. You at index n over 2, or plus or minus 1. You grab that thing, and that must be your answer, right? So there's an n log. We know how to sort n log n time. There's an n log n time algorithm for that. On the other hand, nobody asked us to sort, right? We don't really necessarily. It seems like, well, we can sort to solve the problem, but do we really need to sort to solve the problem? Any other ideas? How about this? I pick one of you, and you tell me your GPA. And we do that partition step from quicksort. All right? And at the end of that partition step, there are, let's say, I don't know, there are about 40 of you in here, right? Let's say the pivot person, their GPA turns out to be 2.8. And nobody's embarrassed, so we'll go ahead and do our thing. We end with people with GPA lower than 2.8 over here. We have the pivot person over here, and people with GPA higher than 2.8 over here. Let's suppose there's 10 people over here, plus the pivot person, plus 29 over there, right? Where the median the median GPA must be smaller than 2.8, larger than 2.8, equal to 2.8. Larger than 2.8, right? And we don't have to touch the ones that are smaller anymore, right? That's the crux of this algorithm called Quickselect for solving this exact problem. The general form of it is, like I said, they give you n unordered elements and an integer k in 1 to n. In that example, I said k to be n over 2 for the median, but in general, it could be anything between 1 and n. And the output is the kth smallest element among A. Sometimes it's called the order statistic problem. And so here is a little review of the behavior of the partition subproblem or subroutine that we know from merge sort. Picks a pivot by some mechanism and sifts the remaining elements into two groups. Elements that are known to be less than or equal to the pivot, followed by the pivot, followed by elements that are greater than or equal to the pivot. And let's suppose when we are asked to find the kth smallest element among n, that is the first thing we do. We're going to do a partition, and we are going to assess the results of that partition. So remember, in the partition, we don't have complete control over the size of the two subproblems, right? Or the two sides, the small set and the large set. So let's think about what kind of things can happen. So for the notation for the next couple slides, we'll say, suppose that after the partition, we end up with some number L elements on the left of the pivot, some number of R elements on the right of the pivot, and the pivot itself. And so N is L plus R plus 1. So let's do a little example here. Suppose N is 100. I happen to be looking for the 30th smallest element. And as a result of the partition, it just turns out that there were 70 elements on the left, followed by the pivot, followed by the remaining 29 elements on the right. Question, the 30th smallest element must be where and what? You answered the same question a second ago, so somebody. I'm looking for the 30th smallest. I just hear muttering. Yeah. It's got to be on the left somewhere. And, or you can be a little more specific. You can say it's got to be the 30th smallest among those elements on the left. We don't care about those 29 elements on the right. We ignore them for now, or forever. So, action. Well, recursively find the 30th smallest element on the left-hand side. What else can happen? Okay, suppose it turns out after I'm still looking for the 30th smallest. Turns out after partition step, I have 29 elements on the left side, followed by the pivot, followed by the remaining 70 elements on the right-hand side. Same question, the 30th smallest element must be where and what? You're scratching your head? Go ahead.
It should be the pivot.
It's the pivot itself, right? Because what does it mean? Oh, the 30th smallest element is the element for which there are exactly 29 elements less than or equal to it. Right? So, this kind of must be the pivot itself. We just return the pivot value. And you can imagine there's probably going to be a third case. This is just a little arithmetic to kind of get our head straight here. So if I call my pivot, let's say my partition routine returns an integer, which is, hey, this is the index of where the pivot landed. Right? This is more implementation stuff that you think about if you're actually programming it. So the pivot lands at some index I. For this scenario, I'm saying, okay, let's say I did a partition of n elements in the array zero-based array. And so if the pivot lands at index I, the things on the left-hand side are from index 0 to I minus 1, of which there are I, and all the way up to and including the pivot, that would be I plus 1 elements. And on the right-hand side, and by the way, the pivot stored at a sub I must be the I plus first smallest. And the right-hand side has n minus I plus 1, quantity I plus 1 elements. This is just so we get sure we get our recursive calls right. So let's look at a third possibility. Suppose that after the partition step, we end up with 10 elements on the left, followed by the pivot, and 89 elements on the right. We're still looking for the 30th smallest. What can we say now? It's got to be on the right. Is it gonna be the 30th smallest element among those 89 elements on the right? Yeah, so there's kind of an offset here, right? Because we're throwing away 11 elements, so it will actually be the 19th smallest element on the right-hand side, stating the subproblem exactly in the same form, right? So we basically have the core basis of an algorithm now, right? We know how to do the partition step. How long does it take to do a partition, by the way? It's linear time, right? You're one side to the other. So we'll basically have an algorithm. You know what? I'm going to jump straight to a more real implementation because it's just as easy to understand as that one. This I call Quickselect. The toy implementation. It takes an array of integers. Its input is an array of integers in arbitrary order. An integer n, which tells us how long the array is, and k is what we've been using it as. We're looking for the kth smallest. I have some base cases and some checks to make sure that k is actually meaningful for the given problem instance. The interesting stuff is on the right-hand side, so I invoke my partition routine on my array A. It returns the index where the pivot ended up. If k is exactly I plus 1, that means we found the k smallest, right? Otherwise, if k is strictly less than I plus 1, that means the k smallest must be on the left-hand side, so we recursively invoke Quickselect, same array, but we tell it, hey, you're only considering the first I element. As far as you're concerned, this array only has I elements, not n anymore, right? So the problem size shrinks. That's that second argument, which up here tells the length of the array. We're still looking for the k smallest. This last one here is where we're searching the right-hand side. This is something that you can do in C and C++. You can't do in a lot of other languages, but anybody know what's going on here with, okay, intuitively what do I want to do? I want to search the the right subarray, right? The pivot landed at index I. We know that our answer isn't the pivot, so the subarray we want to search starts at index I plus 1 as far as we're concerned, right? So, what do you think I'm doing here? Like when we did our merge sort code, the subproblems were specified by a low and high index usually, right? I don't have a low and high index, just to show you another way to implement it. Yeah, go ahead.
So the name of the array is the address of the first element, so you're passing in the address of the I plus 1 element.
Yes.
And that's the start.
So as far as the recursive invocation is concerned, it's still just a zero-based array, but that guy's first element is its parents or its caller's I plus 1, first element, or the element at index I plus 1. Even if you choose not to do this sort of thing when you're as a C programmer, you might see it sometimes. And so you see the trick we're doing? So as far as you're concerned, you just have a zero-based array, but it doesn't start where my array starts. It starts where my element at position I plus 1 is. And otherwise it doesn't care. And how many elements are left? Well, I came in with n elements. I'm discarding everything to the left plus the pivot, so that's n minus the quantity I plus 1. And what am I looking for? I'm not looking for the k smallest. I'm looking for the k minus the number of elements that I'm discarding. GH, sorry. Fundamentally, we got the idea, even if some of the plus and minus ones might be a little puzzling at the moment. The big picture's clear. So let's, for reference, I have the partition routine there, just in case you want to take a look. So similarities and differences between Quickselect and Quicksort. We still use the partition routine, so that's still going to take linear time. And the subproblem size depends on the pivot. Unlike Quicksort, we only solve one side, right? When we solve one of the subproblems, we basically throw the other part away. And the subproblem size is somewhere between 1 and minus 1. We don't have, we can kind of try to bias the pivot in a clever, a smart way, but we can never completely rule out kind of unfavorable pivots. So try to do some analysis here. What do you think the worst thing that can possibly happen is, and give me a recurrence relation that describes it? In quicksort, what was the worst thing that could happen? We're talking about how the pivots can kind of conspire against us.
You can see something, take a pivot where all the work is on one side.
Yeah.
So you
For
can
here,
s-
right?
Yeah.
Yeah, so it could be like very close to the minimum or very close to the minimum, maximum, like the first or second smallest, or the largest or the second largest, something along those lines. And we don't get lucky, right? That, oh, that just happens to be the thing we're looking for. We end up searching that large subproblem of size, let's say n-1. So can you take that and turn it into a corresponding recurrence relation? I'll get you started. How many recursive calls does this algorithm make? One, right? And in this scenario of the worst thing that can possibly happen, n-1. And we still do the partition work, right? So that's why that plus n is there. Or t of n is t of n minus 1 plus n. What's this turn out to be? It's quadratic, right? Theta of n squared. And so we're off to some bad news right away, right? Worst case is quadratic, which is even worse than some sorting algorithms, even in the worst case, right? Like merge sort. However, like in the case of quicksort, this is a rare occurrence. In fact, almost vanishingly rare, but still can happen. So if we're talking about this algorithm, there's probably a reason for it, that there must be some performance, some scenarios, or typical performance, which is more favorable. We already did this. Oh, sorry, I didn't do this. Okay, so now this will be a little bit hand wavy. I'll say, because I don't want to spend time on a full expected time analysis, but one observation is when I do the partition, if I end up with an imbalanced partition, it might actually be good news, right? Because I might end up searching the small side. Right? And so if you think, on average, the size of the subproblem that we search is probably going to be about n half n over 2. So this is a quote-unquote typical case recurrence relation. We're still going to make how many recursive calls? Still just one. And if you kind of buy my hand wavy argument that this is fairly representative of what's going to happen in practice, we end up with about t of n over 2 for our subproblems on average. We still do the partition step. You have your clickers today. Let's do this one. CC, if that's.
CC.
Anybody else? Okay, you know the drill. Persuade, be persuaded, revote, because it was basically a tie for the two most popular answers.
Because this is already, this is not sorted. Yeah. Also, now it's a bit. Just basically anything that's less than 1 if it's on the
We're missing a couple. Last call. And a little bit of shift in the right direction. You can unwind this one. We've done this several times now, actually. You can unwind this in your head, basically. You can say, okay, T of n is T of n over 2 plus n. T of n over 2 is T of n over 4 plus n over 2. Sorry, n over 2. Go one more level, you get T of n over 4 plus n over 4. T of n over 4, yeah. So you end up with this summation. All the local work is n plus n over 2 plus n over 4 plus n over 8 plus n over 16 and so on. That total summation is upper bounded by 2n, and so it's linear, which is why this is an interesting and algorithm. Means it, in a sense, it kind of indicates that this must, in a theoretical sense, must be kind of an easier problem than sorting in a way, right? Because what do we know about sorting? You can't sort faster than n log n time, at least in a comparison-based world. There is kind of this discrepancy, though, that might bother you. I'm arguing that on average the runtime is linear, but still there was that worst case of quadratic. That's a pretty big gap. And you might wonder, is it indeed possible to devise a worst case linear time algorithm for the selection problem? The answer is yes. And it is covered in your textbook. You might find it interesting. However, it's not generally of practical utility. It's more of kind of resolving a theoretical question because the runtime constants are quite large. But basically, it also has kind of historical interest because some famous computer scientists, I believe Knuth was involved in figuring this thing out. Basically, it figures out a way of selecting the pivot so that you can kind of guarantee that you'll get a fractional, at least a fractional amount on each side. But the work that you do to figure that out is, it's still within constants, but it's still quite a bit of work, so you wouldn't actually want to do it. Okay, good? Okay, ready for heap review? So this is in the slide, shows the expansion, just in case you wanted to refresh your memory on that, and the master theorem applies to it as well. Everybody remembers heaps and priority queues and heaps from 251? We're going to go a little fast, so let's get started. A priority queue is an abstract data type, which means what? It means it specifies behavior, but not necessarily implementation. It's an object on which you have the following operations. And the binary heaps are a kind of elegant and clever way of implementing a priority group. Okay, so at a kind of bare bones operations on a priority queue. Okay, so the data in a priority queue, it's a collection of comparable items. I say collection instead of set because we can have duplicates. These comparable values we'll think of as priorities. Duplicates are allowed, and our basic operations on a priority queue are insert some element x, hey, throw this in there, delete min, if the queue is not empty, determine the minimum element, and remove it and send it back in, so it's no longer there. Okay? So, what I've described is technically a min queue, but you can imagine there's a complementary set of specification where you call the max queue, where instead of being interested in always grabbing the minimum element, you're interested in the maximum element. It's not too hard. You could configure a data structure in a way that, like the constructor might specify, oh, I want this to be a max or a min, and then maybe instead of having delete min and or delete max, you would have delete top. Not a big deal. If there are multiple elements that happen to be the minimum, it doesn't matter which one gets removed as far as our semantics are concerned. And so, there we go. Now, I'm going to focus on the right-hand side of this table. So let's suppose, let's suppose you have something like an AVL tree or a red-black tree that guarantees logarithmic height, insertion, deletion, lookup, and so on. Could I use that to build a priority queue implementation? The answer should be yes. However, we might have to tweak things a little bit. So normally when in BSTs, or often with BSTs, we're using them to represent dictionaries where there are no duplicates. So we have to deal with that issue somehow. Not a huge deal, but our nodes could have like a counter associated with them as well, like to represent, oh, I don't just have one copy of 17, I have 3 copies of 17. That's not too much of a big deal. So insertion can be tweaked for those AVL and red-black trees to be able to support that in log n time. What about the delete min? If I was using a BST, how would I do delete min to support my priority queue operation? Where's the minimum element? You're ahead of me. You're talking about heaps. This is just a BST.
Oh, left.
Yeah, so I'm saying, okay, the priority queue, that's just an abstract data type. I can support those operations. I don't necessarily have to have, I could have a linked list underneath if I wanted. I could have binary search tree, or I could have the data structure we're going to talk about in a second, which I believe is what you had in mind, which is the binary heap. So in the case of binary search tree, well, the minimum element you find by going left, 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 left until you can't go left anymore, right? And we know how to do deletion, and so you could kind of build it around it. And that's not bad. That's pretty good performance. However, it's not the only way you can achieve that kind of performance, and in practice a little bit better. And we are going to now talk about the binary heap data structure for supporting priority queues. Okay, so a binary heap is a binary tree. It's not a binary search tree. So it has has root, children, and so on. The trees obey 2 properties. First one we'll call a structural property. So we're not going to allow just any old binary tree. Binary trees are going to be as perfectly balanced as possible, and so they're basically going to be complete binary trees with a little bit of caveat depending on how the actual number of elements that we're trying to store. I'll call that a almost complete binary tree. And then there's going to be an ordering property. The minimum element will always be at the root. And you can recursively specify to just say, okay, the minimum elements at the root, and the left and right subtrees are also heaps. That's the structural property. So every level of a complete binary tree is full. Right? So a complete binary tree of, drop the picture. This is a complete binary tree of, what's the height of this tree? It's easy to be off by 1 on this. 3. 1. How many hops from the root to the leaves? 1, 2, 3. Right. And it's complete because it has the maximum number of nodes possible among all height 3 binary trees. And how many nodes is that? Well, we could literally count them here. It is exact. I'll give you a second. In general, done this before actually. I'm not trying to suggest that this is something you should memorize, but it's something that comes up so often that, yeah, go ahead.
to the n plus 1 minus 1?
Everything's right except I think you meant h instead of n.
Or? Oh, yeah.
Okay. 2 to the h plus 1 minus 1. For quote unquote almost complete binary trees, well, what does that mean? It means for a genuinely complete binary tree, the number of nodes is a power of 2 minus 1, right? Well, I'm not always representing a power of 2 minus 1 elements, so sometimes I might want to have, less elements. Or more, somewhere in between. And so we have a way to represent an arbitrary number of elements, but we still have exactly one topology or one tree that corresponds to that number of elements. So when I say almost complete binary tree, what I mean is every level is full, top to bottom, except maybe the last level, which is still filled left to right. Okay, we'll see the consequences of this in a second as to how we're going to represent this tree in an array. Okay, so the result is, unlike binary search trees, like if I say, okay, even AVL trees, among all AVL trees with 20 nodes, there are lots of them, right? There's lots of different AVL trees with 20 nodes. For us, for our context right now, for a particular n, there is exactly one topology for that n. Okay, so here's for n equals 6, here's for n equals 11. Let's talk about the ordering property, and then we'll talk about our embedding strategy. Okay? So the ordering property is really a partial order. Sometimes binary heaps are called partially ordered trees. The root element is the minimum, and the left and right subtrees are also heaps, which in terms of x, so if x is at the root, y and z are its immediate children, what can we say? Y is greater than or equal to x. It could be equal to x. Z is also greater than or equal to x. Scan this a little bit. There's transitivity involved, right? So if the left and right subtrees are also heaps, well, any descendant of y, for example, q, is less than or equal to y. Sorry, greater than or equal to y, which in turn is greater than or equal to x. And so in this diagram, what's the relationship between p and x? It's a mini. Yeah, I did the same thing. It's greater than or equal to x. How about can you say anything about the relationship between y and z? In general, no. This is not a binary search tree. All we know is that, well, in this case, they happen to have the common parent, but which one's larger and which one's smaller, we don't know. Same thing for p and q. So that is nothing. Okay. Okay, so here are, when I say a topology, I mean the structure of the tree itself, not necessarily the contents of the individual nodes. Okay? So these two things have the exact same topology. They have 11 nodes, and they actually have exactly the same data. But they're not assigned to the same nodes, and they're still both valid heaps. Okay, so I'm not saying that for a particular set of data, there's only one tree and one assignment of the values to the nodes of the tree. What I'm saying is that there's only one structure, but there are probably multiple ways you can assign the values to the different nodes in the tree. So since it's the same data set, well, they're both going to have the same minimum, right? Both have a 7 at the root. The second smallest element has to be probably one of the two children, right? So 11, it's 11, same data set. Happens to be a left child in this on the left diagram. Happens to be the right child in the right diagram. I don't know, other observations. As far as the ordering property is concerned, leaves automatically obey the ordering property because they don't even have any children, right? I work my way bottom up in this tree. I can verify that this subtree is a valid heap. Why? Because these two are leaves, and therefore they're heaps, and 12 is smaller than both of its children. 33 is smaller than both of its children. 11 is smaller than both of its children. 50 is smaller than both of its children, and finally 7 is less than both of its children. Those comparisons verify that it obeys the heap property, or the ordering properties. I'll let you verify the one on the right on your own if you want a little practice. Just one more observation though. This data set has a duplicate, so 55 appears twice. They happen to be siblings in that right diagram. They're kind of far apart in this other diagram, but as long as the order and property holds, it doesn't really matter. Okay. That's all a little abstract so far. We're going to build a data structure for this now. And one of the neat things about a heap-based implementation is that we don't really need pointers. We're going to embed these things in arrays. So our convention is that we will, I have an array. I'll store the root at index 1. Right? And for a node at some index I, greater than or equal to 1, its left child, if it exists, will be at index 2 times I, and its right child will be at 2I plus 1. And so no pointers here, right? This is just arithmetic. As long as I know the position of my current node, some index I can, just a little arithmetic, I can find my left and right children. Okay, so let's go through this. This is one of our 2 trees from the previous example. Here is an array. I have 11 elements in this tree. I have an array that is, so I'm not going to use index 0. If you search online, you might see variants of this where they shifted the root to be at index 0. Fundamentally not any different. Just you got to do a little arithmetic to get it shifted. But for us, we're going to start at index 1. And let's follow the rules. So the root from the diagram is 7, right? And where does the root go? It goes in index 1. And I'm going to do a traversal of this tree. And every time we arrive at a node, we're going to kind of figure out where we are. Okay, so the left child, which stores the 11, must be at index 2 times 1 is 2. So there must be an 11 there. If I continue in a pre-order traversal, so I am at index 2 right now, my left child must be, don't be shy, just 2 times 2 is 4, right? Okay, so that means that 12 is going to be stored there. At index 4, its left child must be at index 8. So there's 21 right there. That guy is a leaf. Our pre-order traversal would end up visiting the right child of the 12, and that will be at index 9. Observation, siblings are always adjacent to each other. Okay. Working our way back up to the node containing 11, which is at index 2. Its right child is at index 5. 2 times 2 plus 1, and it contains 33. Starting to see the pattern here. So 80 is the left child, is going to be the left child of the 5, index 10. Its right child is at index 11. 34, little observation here. That guy's at the lowest level, kind of furthest to the right. Also happens to be at index 11, and there are 11 elements. We'll talk about that in a second, but that's not an accident. My traversal then goes all the way back up to the root. The right child of the root will be at index 3, which is just waiting there to be filled in with the 50. 50 is at index 3. Its left child is at index 50, which has the 51. Right child at index 7, which is storing the 55. See the mapping? Okay. Notice I have 11 elements, and they populate exactly indices 1 through 11. Kind of a nice property. I don't have to worry about holes or anything like that, which is one of the benefits of restricting ourselves to just these almost, what I've called almost complete binary trees. Right? Every level is full top to bottom, except maybe the last level, but that last level is filled up left to right. Right? Another consequence of this is, so this is the same thing. If I look at this tree and I read off the elements top to bottom, left to right, like 7, 11, 50, 12, 33, 51, 55, and so on, like is indicated by these arrows. 7, 11, 50, 12, 33, 51, 55. It's exactly the order they end up appearing in the array. So, this is, an exact representation of this. There's a one-to-one correspondence. I can go back and forth, easily, as far as like drawing diagrams and so on, but all I really need is this thing. Okay. So, this is our embedding strategy. These are some C-defines expressing that, except the bottom one is left blank. So I know how to, for a node of index I know how to find its left child, I know how to find its right child. Can I find its parent, if it has one? Given I? How? Okay, so on the right children are odd, left children are even. So I'm doing, basically I'm doing multiplication, I'm multiplying by 2. In one case I'm multiplying by 2 and adding 1. What's the inverse of multiply by 2? Divide by 2, right? And because it's, standard programming language, integer division semantics for the right child, the fractional part's going to get dropped off, right? So it's like, let's say 6 and 7, they're siblings, right? 6 divided by 2 is 3. 7 divided by 2 is 3.5, but integer division is going to drop off that 0.5 part. Hey, you have the same parent. That's convenient. Once again, no pointers necessary. I can walk up and down the tree to my arc's intent without really having any extra storage. Just a little bit of arithmetic. Okay. Array embedding properties. If I have n elements, they will always occupy indices 1 through n. My array capacity might be larger, right? My heap might grow and contract a little bit over time. I might, so like the yellow part, that might be my little extra overflow buffer space for, as my heap grows, so I might keep track of the capacity of it. But fundamentally, this is the property I want to focus on right now is, that there's no getting around it. There's no holes. I have 11 n elements. They will populate indices 1 through n. Okay. We need to be able to do something with this data structure though, right? So we wanted, what are our 2 operations from a priority queue? We want to be able to support insert, and we want to support delete min. Just do something really easy. So some libraries and collections classes will have, for a priority queue, might have an operation sometimes called peek or peek min, which is distinct from delete min in the sense that it just reports to you what the minimum element is, but it doesn't remove it or modify the data structure. It's still the data, collection of elements is still the same. How could we support that with this kind of data structure? It's one liner, right? Unless it's empty, in which case I have some other condition that I, flag that, there's no answer to your question. Otherwise, I'm just going to return a sub 1 if my array is called a. Let's talk about insertion. So I have this configuration, and it's a valid heap, and I want to insert 25. I have 11 elements right now. At the end of this process, I'm going to have 12, right? What did we just say? If I have n elements, they're going to occupy indices 1 through n. In this case, they'll occupy indices 1 through 12, which means something's going to end up there, right? Not necessarily the thing we're inserting in the end, but something's going to have to end up there. And there's not going to be any action outside of that window. So it's a pretty straightforward idea. We are, so I know where that slot is, right? So I know n. I know how big my heap is at any point in time, right? So I know that when I do an insert, that's going to go, it's position n plus 1 where something has to happen. So let's suppose I plop that 25 down there for at least for a moment. And I'm going to do an operation commonly called percolate up or bubble up. And what we're going to do is we're going to look at that guy's parent. We know how to find our parent, right? We know our index. And for the sake of argument, suppose that I did an insert of 70. And I did exactly this, and I looked at my parent and said, oh, I'm bigger than 51. I'll just stay right here. We agree we have a valid heap, right? Now let's look at this case where that's not true. 25 is smaller than the parent, and I'm going to do a swap. At least conceptually, I'll do a swap. In implementation, you will kind of just pull things down and then plop the thing you're percolating up at the end, but that is, we'll see that in a second. And now what do you think I should do? Same thing, right? So now, okay, 25 versus my parent, which is storing 50. 25 smaller, I'm going to swap them. I'll pull up the 25. An observation here is the 25 is also smaller than the 55 on the right side, right? Do I need to check that explicitly? No, I don't, because I get it from basically transitivity. 50 was, so 50 is less than or equal to 55 just by virtue of it having been a heap at the beginning, right? So the parent is less than or equal to the right child. The thing that I'm bubbling up is less than the parent. Therefore, it's automatically less than the right child. I don't need to do anything to confirm that, even if there was a big giant tree hanging off there. Okay, so got the 25 up to there. We're going to do one more test. Oh, I've bubbled up to where I need to go. I don't go any further, and the 25 just lands right there. We're done. Okay. Could have gone all the way up to the root, given us a new minimum. How long do you think that should take in general, in terms of n? Log n, right? Logarithmic. Our trees are as balanced as they possibly can be. All of the action is on a particular path from a leaf walking up towards the root. The worst thing that can possibly happen is if I walk all the way up to the root, I'm going to examine, therefore I'm going to examine the most log n nodes, right? Not doing anything off that path. And so after insertion, now we have 12 elements, and we are ready for our next operation. Okay, now dealing with trees. You've done a lot of stuff with trees, I know. Traversing trees, you need to not only be able to figure out who your children are, but also things like, am I a leaf? And those sorts of properties. Do I even have a left child? Which oftentimes we'll do by testing for a null pointer. We don't have any pointers here, so let's do a little bit of practice. Figuring out, if I know two things, I have a heap, it's embedded in this array, and I know how many elements it has, n. Okay? And I'll call my array h. So given n, I have my heap array h and an index I. I want to answer the question, hey, does index I even correspond to a node in my tree? It's not a pointer, so I can't compare it against null, but I have enough information to figure it out. Well, what did we say? If I have n elements in a heap, they occupy exactly indices 1 through n. So it corresponds to a node in my tree. I has to be strictly greater than 0 and less than or equal to n. Not too hard. Something a little more interesting. How about so let's suppose I have an index, and I know it is an actual node in my tree. And now I say, okay, is this thing a leaf? What condition, how can I test for that? So if it was a regular structure with left and right pointers, what would I do? If t follow left equals null and t follow right equals null, then I must be a leaf, right? I don't have that stuff, but go ahead.
So I is greater than 2 to the 8.
I only know these two things. I only know n and I. And for this little exercise, let's suppose we already know, we've already passed the first test. I is actually a node in the tree. In other words, I is between 1 and n inclusive. Am I a leaf or not? Gentleman in the black there. But, yeah, yes.
You would just check if it has a child, so you just multiply and see if it's an array.
So, well, if I have a child, a left child, it's going to be at index 2i, right? And if I don't have a child, 2i is not a node in the tree, right? So then that means that 2i is strictly greater than it. So once again, we don't need to add any pointers or anything like that. We can figure all this stuff out. We can do recursive traversals of these trees. What else? How about this one? The condition under which, so that index I does correspond to a node. It passes that very first test. What is the condition for it actually having a left child? If it has a left child, it will be at index 2i, right? We already know how to determine if an arbitrary index is part of the tree or a node in the tree.
So it would be the same one, except less than 3.
Yep, if 2i is less than or equal to n, now I have a left child. If I had condition for having a right child, shouldn't be too surprising. 2i plus 1 is less than or equal to n. Okay. How about, do I have a parent? If I have a parent, I know it will be at I over 2, but I mean I have a parent. Who doesn't have a parent? The root, right? It's index 1. And if I'm presuming that this is already a valid node in the tree, every node in the tree has a parent except the root itself. And so if I over 2 is greater than 0, that means, oh, it's actually part of the tree. That means I have a parent. Okay. These exercises are so when we go to actually coding up some of this stuff, we know how to think about, conditions for when to stop. Okay. Code. This was 251. I'd have you get together and try to write this. So let's just jump to it. This is percolate up. Okay, so my percolate up function takes my array h and an integer I, which is the index of from which I'm supposed to do the percolate up. Okay? So it presumes everything up to index I minus 1 represents a valid heap. And we're going to do what we did kind of pictorially a minute ago. So x is what's currently stored in h sub I. That's the value that's being percolated up. So by the way, like bubble up, I don't know. You can think of these as like objects of different density, right? Things with small density are low value, right? But low density things tend to float up in a big pool of stuff, right? And high density things tend to sit toward the bottom. And this is the thing that was just kind of jammed into our big bucket, at the bottom, right? And maybe it's going to float up to the top. That's x. So x is at position I. I'm supposed to bubble up from there. If I have a parent, my parent will be at index I over 2. So I'm going to have these two things kind of moving in lockstep. I don't really need both variables, but I have both variables. And so while in my while loop, while p is strictly greater than 0, in other words, while I have a parent and the value stored at that parent is bigger than me, I'm smaller than the value stored at that parent, right? X strictly less than h sub p. What does that mean? It means, oh, I got to keep going, right? And what that really means is I have to pull down the larger things. So inside the body of the loop, h sub I, which is the child, gets assigned the value of its parent, which is h sub p. And to get ready for the next iteration, I becomes p, and I update p to be the old i's grandparent, right? If it exists. The end of this process, what do I have? I haven't assigned x anywhere. The claim is that at the end of this entire process, I is exactly at the position where x belongs, and so then I finally do that assignment. So like the animation was kind of like a sequence of swaps, but this kind of bypasses some of that. It does pulls all those guys down, and then when it figures out where the new element belongs, it just assigns it. So far, so good? Okay? And even if you didn't know anything about trees, if you looked at this, and let's say I was n, if you just kind of looked at this, say, okay, I start out at n, and through this loop, I'm always dividing by 2, right? How many times can I do that before I get down to 1 or 0? That's our log n, right? Same old story. Okay. All right, so we know how to do an insertion. It's not very useful unless we can do delete min as well. So let's talk about delete min. Here's a configuration for the previous example. We know that that 7 is going to be, removed and sent back to our caller one way or another. It also means I have 12 elements right now. After the delete min is done, I will have 11, right? And therefore, those 11 elements will have to occupy exactly indices 1 through 11. What's sitting in index 12 right now? This guy. Sometimes I call this like the rightmost leaf, right? Which is also the rightmost entry in the array. So we've got some stuff to figure out. And what kind of observations can we make? Well, one observation is we know that the new minimum has to be one of the 2 children, right? In this case, it happens to be the left child, the 11. So you want to walk through an idea that doesn't quite work? Let's suppose I did this. So I know that 7 is going to go away, and so I'm going to treat that slot kind of like a hole that has to be filled somehow. And I look at the children, I say, okay, the 11 is the smallest, I'm going to fill that root slot with that 11, and effectively push down the hole to that left node. And now I've got to reconcile that on the left-hand side. So I have a 12 and a 33 on the left for the children of that node. The smallest of those is the 12. So let's say I pull up that 12 to where that 11 is, and I push the hole down to here. Same thing again, I have a 21 and a 55. I pull up, the 21 is a smaller one, I pull that thing up to here, and now effectively that hole has been pushed down to this slot. Problem is that it's a hole, right? Nothing really belongs there, and we really, by construction, we want this thing to be contiguous from left to right. You could, if I was more clever about constructing my example, this wouldn't work, but you could, at this point, you could say, oh, well, I know this guy's a problem. That can't stay there. I just put this over here. Kind of got lucky in this case. This doesn't always work. That one isn't necessarily bigger than that one up there. So that's kind of cumbersome and doesn't even always work, but it captures some of the ideas. A slight refinement is to not have a hole. We're going to pull, we know that 51 has to go somewhere. We're going to, at least conceptually, we're going to hoist it up to the root right at the beginning. And what do we have? We have 2 subtrees that are valid heaps, right? They obey the ordering property. And we're going to do an operation commonly called percolate down from the root. Effectively, this is no longer part of the heap anymore. That 51 is going to end up being somewhere in among the first 11 slots. And now we're going to do the same basic idea. I look at the 51. We're at the root. In this case, it has 2 children. I look at the smaller of them. The smaller of them is an 11, which is smaller than the 51. I'm going to pull up the 11 and push down the 51. Repeat. Here I have 12 and 33 as my children, and I will identify 12 as the smaller of them. I will also observe that 12 is smaller than my 51, meaning that the 12 gets pulled up, 51 gets pushed down. Same story here. 51 the 21 is the smaller of the 2 children. It also happens to be smaller than the 51 that I'm pushing down, and I end up with this configuration. How long do you think that's gonna take us? Also logarithmic, right? I go, starting from the root, I examine my two children, but I don't, kind of go in both directions, I only go in one, depending on where the smaller of the two was. And the worst thing that can happen is that goes all the way down to a leaf, and the amount of steps that will take is determined by the height of the tree, which we know is logarithmic. It's not hard to implement, but it's, you have to be a little bit careful and making sure you consider all of the scenarios. Here's a wrapper function for delete min, which it grabs the value that's being deleted. That is at index 1. That is x. It will ultimately be returned. This line right here, what does it do? H sub 1 gets h sub n. H sub n, we're going from n elements to n minus 1 elements. So that thing kind of gets hoisted up to the root. And then I invoke percolate down from the root. And now effectively, by the way, I have only n minus 1 elements, right? That's why that second thing's there. And here is an implementation of percolate down. So if you think about it, when you're at a node, you say you're doing percolate down, you have to say, do I have any children? First of all, right? So I know when to stop. If I do have children, do I have only one child or I have two children? And in the case I have two children, I want the minimum of those two children to see if it's smaller than me. Right? Remember what we're doing? How does this need to be swapped with one of his children, right? So kind of, okay, how many children do I have? If I have two, figure out the smallest of them, compare that with the thing that I'm percolating down. If it is indeed smaller, do the swap, and then keep going. Right? So those possible cases, I don't know, I wrote it this way because the issue of determining what to do with your children, super complicated, but there's a couple of situations you need to consider. So this little function called minchild idx takes a root index and asks the question, determines the smallest of its children as an index. Well, it might not have any children, so by convention I return -1. Say, hey, you don't even have any children. And otherwise it has at least one child. And so you can see there, if my left index is greater than n, return -1. Otherwise, if left equals n, what's that condition? If left equals n, that means I don't have a right child. So there's potential for examining something that's outside the bounds of the heap. These are just details, basically. So if I don't have a right child, or my left child is less than my right child, I return left, otherwise I return right. Fundamentally inside this, I say, okay, what's the index of my smallest child? I call that function to figure it out. While that is not -1, I have at least one child, and h sub min, the actual value of my minimum child, is less than x, the thing that I'm percolating down, what do? I pull up the thing from the min child into I. H sub I gets h sub min c. I becomes min c. I walk down that direction, whether it's left or right, and I get ready for the next iteration by invoking min c. Min child index. Maybe not the way you would do it, but fundamentally you kind of get the idea, right? We're walking down the tree, and we're careful to make sure we, figure all the cases. 0 children, 1 child, 2 children. Right? So a little trickier to implement than percolate up, but still totally doable. And we agree it should be logarithmic runtime? Great. Okay. We have most of the guts that we need. Let's talk about a related problem. Yeah?
Just a question. Since, are we assuming we have a dynamic array?
So good question. By dynamic array, I think you're saying something like a C++ vector or something that we're automatically resizing ourselves. Because I kind of wave my hands at, okay, at any moment in time, these are the things that are in the heap, and the array itself might be bigger. There might be some more space out there. You definitely could implement it in a way where you would resize if so you have two things, your current number of elements in your heap and the current capacity of your array, right? And if you get an insert operation that you've exhausted the capacity of your array, you either have to say, sorry, I can't do it, or you have to do something else. And the typical thing is to allocate another array twice as large, copy stuff over, and then go on about your business. That's perfectly fine and doable. You can do it indirect yourself. You can do it indirectly through a vector. However, kind of most of the the key applications where heaps are popular to use, oftentimes you have an upper bound on that already, and so you allocate an array initially that has enough capacity. When we talk about graph algorithms, in particular Dijkstra's algorithm, the number of vertices in the graph is going to determine the maximum size of your heap, and so you just initialize it that way in your, which is why, for a robust class implementation of this, you definitely would want to use it. Okay, yeah.
Second question. So then, when you delete an element,
Yeah.
do you like zero it out, -1 in there?
Don't care.
Don't care.
Because this just jumped at the end, overflow, the part of the array that I'm not using. Later on, if I use it, the first thing I'm going to do is I'm going to assign a value to it. I know everything I need to know about it, that slot, just by the virtue of the fact that I know how big my heap is. Right? And there's no magic thing to put there anyhow, right? If they're integers, well, 0 is a perfectly valid thing to be in a heap anyhow. But that is a good question, which is also why I didn't scrub it out, right? It still stores a 51, but that 51 doesn't mean anything to anybody. Let's suppose I give you n elements. I give you an array, n elements populating indices 1 through n, but in some arbitrary order. I don't want them sorted. I just want you to rearrange them to form a valid heap. Okay? Well, this is the build heap problem. We already have some tools to do this, but there's a couple different ways we can put things together. One we'll call the top-down approach, and another we will call the bottom-up approach. Remember percolate up? Right, so I have a function td build heap, top-down build heap, array h, integer n. It's already been populated in indices 1 through n. And take a look at that code. What is it doing? It's going from 2 up to n inclusive. And for each of those, it invokes percolate up. This is really the same as doing a sequence of insertions, effectively. That might be a little puzzling, but this picture might help clarify it. Notice that I started at index 2, right? And the idea is, oh, well, the element just stored at index 1 on its own. Well, that's a heap of size 1, right? So I'm not going to touch it right now. I'm going to do a percolate up from index 2. Might get pulled down. Right? And at some intermediate stage, what I have is all this gray stuff here. This gray, that's already been turned into heap. Let's say up to index, 55. Now I'm at index 56, and I'm launching percolate up from there. Okay? Finally, I get down to n, and that's my last percolate up, and I now have a heap. Okay? Make sense? Alternatively, though, what's another tool, weapon or tool in our whatever toolbox is percolate down. So another way, so take a look at this code for a second. So I'll call it bottom up BU build heap. Takes the same parameters. I'm going to iterate through some entries in my array, but I'm not going left to right starting at 2. I'm going from right to left. And where do I start at? I start out at n over 2. So what's at index n? Index n is what I've been calling the rightmost leaf, right? And then therefore n over 2 must be the parent of the rightmost leaf. And I gets decremented, and for each one of those entries, I'm going to invoke the percolate down. So what's really going on here? Here is that tree, and of course corresponds to its array corresponding array embedding. I've made all the leaves green because just similarly to how we started the other one, we said, oh, the singleton guy at index 1, that's a heap, right? We can also think of these little singleton guys, they're little heaps, right? As far as the ordering property is concerned, right? Because they don't have any children, so they're little heaps of size 1. Where is the nth element? The rightmost leaf is right here. Its parent is that guy, so you could say that's like the rightmost leaf, the rightmost non-leaf. And what does the loop do? It starts there and goes backwards, right? Reverse layer by layer, right? And what does it do at each of those nodes? It invokes percolate down. Turns that little group, so what's the property? It's left and right subtrees or heaps, right? Invoke percolate down from the root, it turns it into a height 1 heap. Does this one, this one, this one. Working its way back, and then it gets to something a little bigger, and we have the same property, right? Those two subtrees are heaps by virtue of the previous invocations of percolate down. And so I do percolate down from the parent. I've turned that entire thing into a height 2 heap. Same thing here, same thing here. And all the way up to the root. And at that very last step, left subtree is a heap, right subtree is a heap. Percolate down turns the whole thing into a heap. Okay. Get the idea? Basically why it works. Now, we don't have to think of it this way. Let's say an equivalent way to present this idea it would be recursively. So this thing's a tree. I can traverse it. I know how to determine if I have a left child, a right child, and if I'm passing a node as a part of a recursive call, what do? I pass the index and so on. So another way of thinking of this procedure is recursively. So if I start at the root and I say, okay, turn my left subtree into a heap recursively. Turn my right subtree into a heap recursively. Then after that, I'm at exactly the same state I am right here, right? Now do percolate down to turn the whole thing into a heap. It's really the same principle, it's just that it will do the percolate downs in a slightly different order. Right? It'll turn this whole left side into a heap and the whole right side. You're rustling around, which makes me think it's almost time to go. Let's ask a quicker question real quick. So I have these two different ideas. Is there anything more than like a aesthetic difference between them, or is there a quantitative difference? Is one faster than the other, effectively? What's your intuition? Top down faster, bottom up faster, or they're just two ways of solving the same problem and they're asymptotically equivalent? While you're thinking about your answers, I will make a comment that don't be confused. So remember, a top-down build heap uses what subroutine? Percolate up, which can be kind of confusing at first glance, right? It's called top-down though because it's building from the root and expanding it going top-down. The fact that it happens to be using a percolate up routine to do it doesn't mean it's the bottom-up procedure. The bottom-up procedure uses percolate down, so don't let that, throw you off. Let's see what people are saying. Interesting. Okay. No majority. Turn that bottom up faster. Okay. I still have you for one more minute, so we'll sync up with the other section. The recursive version of it that I just described, think about that for a second. And what do we do when we have divide and conquer algorithms? We usually start by trying to write a recurrence relation to describe the runtime. So Let me reiterate what that does. Recursively build heapify my left subtree. Recursively heapify my right subtree. It's basically perfectly balanced, so there's going to be about n over 2 elements in the left subtree, about n over 2 in the right subtree, right? So if t of n is the time for this entire thing to complete, well, what happens? I do 2 recursive calls to heapify, one for each of my left and right subtrees to heapify them, each of which contain about n over 2 elements. What else happens after that?
Percolate down.
Percolate down, thank you. All right, I've got my subtrees are good, my root's probably screwed up, I do percolate down to resolve it. How long does that take? Log n, right? This is a divide and conquer recurrence relation. We're going to fiddle around with it a little at the beginning of class next week, but at least the textbook version of the master theorem applies to this. And let's just get a quick little feel for it. So I have plus log n for my local work. Okay, if it was plus 1, it would be basically the time to traverse a regular old tree, right? If it was plus n, it would be analogous to merge sort, right? So it's plus 1, the whole thing becomes n, right? If it's plus n, the whole thing becomes n log n. We have something in between here. Which way do you think it's going to snap? That's enough to kind of tell us, oh, it's got to be somewhere in that window, right? Turns out it's here. The master theorem will show you that. A little bit of intuition. If you think about the top down, way up here. Think about the top down step. There are about half the nodes are leaves, right? Each one of those leaves is going to have a percolate up invoked on it. And those are kind of the lousy ones, right? Because that's when the tree's tall. And the percolate ups could go all the way up to the root, basically really be log n time. On the other hand, this guy, the time for the percolate down is really determined by the height of the tree on which it is operating. We've kind of flipped it to our advantage. We're doing percolate down on lots of little tiny little short trees, only a handful that are even anywhere close to log n. That's not a proof that it turns out to be linear, but it's maybe a little bit of intuition as to why they might not turn out to be asymptotically the same. Right? I'll let you go. Dynamic programming for probably like the next 3 weeks. We're going to start that Tuesday, even if we do a little wrap up of this stuff at the beginning.